Alright, chemistry, let's get started on our combined section. Chapter 6 is sections 1 and 2. Let's look at our introduction to chemical bonding. In this section, I want you to be able to define a chemical bond. I want you to be able to describe and differentiate between ionic, polar covalent, and non-polar covalent bonding. I want you to be able to calculate and classify bonds according to electronegativity differences and identify the percentage of ionic character of any bond using electronegativity differences. All right, let's go. Let's start with our definition of chemical bond. It's a mutual electrical attraction between the nuclei and valence electrons of different atoms that bind atoms together. So we have an electrostatic attraction, right? That's pluses attracted to minuses and minuses attracted to pluses. But the attraction is between the positively charged nucleus of one atom and the negatively charged valence electrons of another atom. That is the source of the attraction. We classify the different types of bonds according to the way the valence electrons are distributed around the nuclei of those combined atoms. So, the first type of bond that we're going to cover is the ionic bond. It's a chemical bond resulting from the electrostatic attraction from cations and anions. It makes a lot of sense. In order to have an ionic bond, we need to have ions in the first place. So it's going to be the electrostatic attraction between positively charged ions and negatively charged ions. It's still pluses and minuses. Now, in a perfect ionic bond, one atom completely gives up one or more electron to another atom, which pretty much does not happen. But in the idea, the illustration would be element A plus element B reacts to form the ion, the positively charged cation of element A, and the negatively charged anion of element B. So let's take a look at this. So we have sodium here on the left forming its positively charged cation. We know that sodium is going to form a +1 charged ion because it has one valence electron. It's in group number 1, so it's got one valence electron. And in order to satisfy its octet, the best strategy is to lose that one valence electron, as we see it doing here in this animation. After it loses that one electron, it will have a +1 charge, a positively charged cation. Now that that electron is on the loose, okay, it has been jettisoned from sodium, it can fall into the hands of some atom that is around trying to gain an electron. For example, fluorine wants to accept one electron. If there's a free electron, say around sodium, fluorine will take that electron off sodium's hands. Now that fluorine will be a fluoride ion, it'll have a -1 charge. Now that we have a positive charge and a negative charge, there's going to be an electrostatic attraction, and those two bond together. So let's take a look at covalent bonds. A covalent bond is a chemical bond resulting from the sharing of valence electrons, not the transfer like we saw in the animation. It's the sharing of valence electrons between two atoms. Why are they sharing electrons? In order to satisfy their octet, right? They're trying to achieve that noble gas electron configuration and obtain stability. So in a pure covalent bond, the electrons are shared equally between the two atoms. We call this a nonpolar covalent bond. There's going to be little to no electronegativity difference, so the strength with which the nuclei of these atoms are pulling on the electrons is going to be the same. So neither one is going to win that tug of war. The electrons are going to hang out right in the middle between those two nuclei. But most covalent bonds result in the electrons being shared unequally between the atoms, which we call polar covalent bonds, because most of the time there is at least some electronegativity difference between the two atoms that are bonded. That means that one atom is going to be able to pull harder on those electrons in the bond, making those electrons lean a little bit closer to that more electronegative atom. Again, we call that a polar covalent bond. Let's look at a nonpolar covalent bond. Here we have two atoms that both have 7 valence electrons. They're just one away from being able to satisfy their octet and obtain a noble gas electron configuration and the stability that it affords. But they have to gain one electron. So both of these elements are clearly very electronegative because they have 7 valence electrons. They only want to gain one more. The strategy is definitely to gain one more, not to lose 7. So since both of them have the same electronegativity, it is very difficult for one to outpull the other because they are the same in that respect. And so the best way for them to both achieve their octet, their noble gas electron configuration, is to share their unpaired electrons there and form a covalent bond. And you'll notice after the bond has been formed that if you trace those outer circles that represent the valence shell of each of each atom. Each atom now has 8 valence electrons. You satisfied the octet. We have a noble gas electron configuration and the stability that comes along with it. That doesn't only happen with elements that have 7 valence electrons. What about oxygen here that has 6 valence electrons? Right, we share 1 pair, but that's not enough. We don't have an octet, so we actually have to share a second pair. So we create what's called a double bond. We're actually sharing between each other 4 different electrons. These two, right, that's a 1 bond, but each oxygen still doesn't have full octet, so we take yet another set of unpaired electrons, and we involve them in a bond and share those as well. So we result in a oxygen-oxygen double bond that is covalent. Now, it is true that there is no bond that is completely ionic, and it is pretty rare to have a completely ionic bond. Now, completely covalent bonds do happen, okay, but most of the time, most bonds range between these two extremes. They range somewhere in between totally ionic and totally covalent. Now, the degree of ionic or covalent character can be estimated by comparing the electronegativity values of those two elements. The greater the difference, the more ionic the bond. For example, if we calculate the difference between the two electronegativity values and we find that the difference is somewhere in the range of 1.71 to 4.0, we consider that bond between the two atoms ionic, as an ionic bond. For example, what if we were going to try to bond cesium and fluorine? Well, fluorine has an electronegativity value of 4.0, cesium has an electronegativity value of 0.7, so the difference is going to be 3.3. That's going to be right smack dab in that ionic range. We can conclude from this that cesium is going to become the cation, fluorine is going to steal that electron from cesium, and cesium will therefore become the anion. Well, the question is, are you saying that we are supposed to memorize all of these electronegativity values? And the answer is no, you do not have to memorize any of these electronegativity values. You will always have access to this information. Just like when I gave you your periodic table, I told you do not bother memorizing anything on this table. I'm giving you this table so that you do not have to memorize anything on the table. I'm going to be assessing how you use that information. That is what we're learning, how to use the information. We're not trying to memorize stuff on the table. Same thing goes with the electronegativity values. You will either have this available for you during all assignments, and I will print this for you on the quiz that you take for this section. You will always have access to this information. Now, moving forward, when we have a bond that is between two identical atoms, meaning I have 2 bromine atoms, or I have 2 iodine atoms, or maybe 2 nitrogen atoms, I have a pure and completely covalent bond. Now, I have all of these elemental symbols listed out for you. Notice that they create a mnemonic, Brinkelhoff. Brinkelhoff is a mnemonic that helps you remember what atoms do this all the time. Bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine all will form diatomic molecules, meaning when you have pure bromine or pure iodine or pure nitrogen or pure chlorine or pure hydrogen or pure oxygen or pure fluorine, it's going to be Br2, I2, N2, Cl2, H2, O2, or F2. For you to have a molecule of any of these 7 elements, to have one molecule, it requires 2 atoms, right? Diatomic molecules. And so that's going to lead us into our types of covalent bonds. We have the nonpolar, like we see up here with those completely and pure covalent bonds. It's a covalent bond in which the bonding electrons are shared equally by the bonded atoms, with a resulting balanced distribution of electrical charge. Now, why is the electrical charge evenly distributed? Because there is no electronegativity difference, meaning the strength with which those atoms, those nuclei, are pulling on valence electrons is the same. It's like a tug-of-war between 2 people who have the exact same strength. The flag in the middle of that tug-of-war is not moving. Those electrons are right smack dab in the middle on average. Now, we can know that we're dealing with a nonpolar covalent bond if we calculate an electronegativity difference that is between 0 and 0.3. If we see that the electronegativity difference is small in this range, we will conclude that it is a nonpolar covalent bond, and we will also conclude that this bond shows anywhere from 0 to 5% ionic character. Let's take a look at another animation. Here we have 2 hydrogen atoms bonding to form a hydrogen molecule, right? Hydrogen is one of the diatomic molecules, and so when you see pure hydrogen, it's in the form of a hydrogen molecule, which is H2. Now, as these hydrogen atoms are by themselves, they just have one electron that's zooming around in that electron cloud, but as they bond, okay, as they form the H2 molecule, the electrons start to spend more time in between the two nuclei because they're being shared by the two nuclei. And as these electrons move around, you'll actually see that they do spend some time on the outer edges of the two nuclei. They do spend some time out here, but it's a very small amount of time. It's very short-lived. On average, they spend most of their time right here in the middle, evenly shared, on average. It's true that those electrons are moving around, just like those red dots are showing. They are moving around, but their average position is right in the middle between those two hydrogen atoms. Now let's look at polar covalent bonds. Now when I say polar, I'm using the word pole as the base. Pole simply refers to an unequal distribution of charge. Okay? Polar covalent bonds are bonds where the united atoms have an unequal attraction for the shared electrons. Now the electrons are still shared, but the electronegativity difference is starting to creep up a little bit, meaning one element has the ability to attract the electrons a little bit more strongly than the other one. Now, not so greatly that it completely transfers the electrons and forms an ion, okay, not quite that strong, okay, but it is strong enough to pull those electrons a little bit closer to one atom versus the other, even though they're still being shared. Now, when you go to calculate your electronegativity difference, if you get a number that lands in the range between 0.3 and 1.7, you're going to conclude that that bond is a polar covalent bond. You can also conclude that that bond shows anywhere between 5% and 50% ionic character. Here's another animation showing polar covalent bonds. Here we have hydrogen bonded to oxygen on the top, and we can see that there is a sharing of the electrons between hydrogen and oxygen. But you can tell by the distribution of those red dots that represent the electrons that those electrons are clearly spending more time around oxygen as compared to hydrogen. Hydrogen does have access to those electrons. You can see that that red dot does go over there every now and again, but most of the time, okay, an unequal amount of time, those electrons are found closer to oxygen. Now, how are we going to do this? Let's give an example of how we actually accomplish this. Oh, I'm sorry, I actually forgot to point out one thing. Let's go back to these animations. Partial positive and partial negative charges. We look down here at this animation in the bottom. We have the hydrogen atom, and then we have the fluorine atom. They come together, they form a covalent bond, but it's going to be a polar covalent bond because fluorine is much more electronegative than hydrogen. Okay, and so just like in this animation up top, the electrons that are also owned by hydrogen are still owned by hydrogen, but they spend more time around fluorine. Now, because those electrons spend more time around fluorine, fluorine develops what's called a partial negative charge, represented by this symbol right here. Okay. Now, it is not a full charge. It is not an ion because this is a covalent bond. There's no transfer of electrons. Hydrogen still technically has access to these electrons, but because there's so much negative stuff over here, it gains a partial negative charge on the fluorine side and a partial positive charge on the hydrogen side. All right, now we'll get to the examples. So if I want to figure out what kind of bond hydrogen and hydrogen are going to show, I simply calculate the difference between the two electronegativities. So that's going to be 2.1 minus 2.1. That's going to be 0. There's 0 difference. That's going to be a nonpolar covalent bond. Well, what about two elements that are not identical? How about hydrogen, still having a 2.1 electronegativity, and chlorine, which is coming in at 3.0 electronegativity? The difference is going to be 0.9. That's going to be a polar covalent bond. Because chlorine here is more electronegative than hydrogen, it is going to have a stronger attraction for the electrons in the bond. Therefore, an uneven pull on the electrons is going to occur. However, the electrons are still being shared. They're not being transferred. This results in a partial positive and partial negative pull. All right, let's finish up with metallic bonding. Now, metallic bonding is going to occur, obviously, between metal atoms. And this is going to happen in the either liquid or solid state because metals tend to give up their electrons, right? They're on the left side of the periodic table. They tend to give away their valence electrons. Now, this is only going to happen because metals are trying to obtain a noble gas electron configuration. They're trying to satisfy the octet rule. But if we have a pure mass of metal, only metals, we only have elements that want to donate electrons. We don't have any elements around that want to accept those electrons. And so what is going to happen is those electrons are going to be donated into this interstitial area in between the metal atoms when they ionize, right, to satisfy the octet rule to become positive cation, but there's nowhere for them to go. Now, they don't leave because the positively charged cations are positively charged and electrostatically attract the negatively charged electrons. Okay, that's fine. So they just bounce around in between the different cations in the sample while never leaving the sample. Okay, we refer to this as the electron sea. These free-moving electrons are called an electron sea, and that electron sea is the reason for any metallic property that you can think of: the luster, the malleability, the ductility, or the conductivity of heat and electricity. So here's an animation representing the sea of electrons within a mass of metal atoms. We see that we have a whole bunch of positively charged cations, right? They've already donated their electrons into the electron sea. And so we have this negatively charged interstitial area in between, right, in between the different cations. But even though these are positively charged cations, they are not truly taking in the electrons into their own electron clouds. They're simply bouncing around in between the different positive charges. Now here is a quick trick I'll let you in on. In order to tell the difference between a covalent bond, an ionic bond, and a metallic bond, or which types of elements are going to form which, here's a little quick trick. It's a little shortcut. If you are experiencing a bond between two nonmetals, that's going to be a covalent bond. If you're experiencing a bond between a metal and a nonmetal, okay, one of each, it's going to be ionic. And if you're experiencing a bond between two metals, that's going to be called a metallic bond. Just a quick trick right there. All right, let's end with a little bit of a check for understanding. Here, I have a huge list of pairs of atoms. I want you to determine the electronegativity difference, the bond type, and the more electronegative element within these pairs. Go ahead and press pause now. All right, let's see what we came up with here. Let's see if your numbers match mine. Let's look at just the first three. Hydrogen and fluorine. Fluorine with electronegativity value of 4.0 minus a 2.1 from hydrogen. That's a difference of 1.9. That makes the bond type ionic. The more electronegative atom is fluorine here. Here we got, for number 2, we got bromine and bromine. Both have an electronegativity value of 2.8, so there is no difference, making the bond type nonpolar covalent. Number 3, aluminum and sulfur. Sulfur coming in with an electronegativity value of 2.5. Aluminum coming in with a 1.5. The difference is 1.0, making it a polar covalent bond. The more electronegative atom is sulfur. All right, guys, this has been your introduction to chemical bonding. We've covered introduced ionic bonds, introduced covalent bonds, and introduced metallic bonds. All right, guys, I will see you next period.